We'll be reading chapter 28, section 2, found on page 753. The moon. The moon is a familiar object in the night sky. Despite its proximity to Earth, however, the origins and nature of the moon have been exclusive. Only with advances in telescope and spacecraft technology over the past 100 years have people begun to understand the moon. Reaching for the moon. Astronomers have learned much about the moon from telescopic observations. However, most of our knowledge of the moon comes from explorations by space probes, such as Lunar Prospector and Clementine, and astronauts. Plans for a crewed lunar expedition began in the late 1950s. The first step was taken in 1957 with the launch of the first satellite, Sputnik 1, by the Soviet Union. Shortly thereafter, in 1961, Soviet cosmonaut Yuri A. Gagarin became the first human in space. The United States project Mercury launched the first American, Alan B. Shepard Jr., shown in Figure 28-7, into space on May 5, 1961. Project Gemini launched two-person crews into space, and on July 20, 1969, the Apollo program landed Neil Armstrong and Buzz Aldrin on the moon during Apollo 11. Lunar properties. Earth's moon is unique among all the moons in the solar system. It is one of the largest moons, especially compared to the size of the planet it orbits. The moon's radius is about 27% of Earth's radius, and its mass is more than 1% of Earth's mass, as shown in Table 28.1. Most moons are much smaller than this in relation to the size of the planets they orbit. The orbit of the moon is also unusual in that the moon is relatively farther from Earth than most moons from the planets they orbit. Earth's moon is a solid rocky body in contrast to the icy composition of the moons of the outer planets Jupiter, Saturn, Uranus, Neptune, and Pluto. Also, Earth's moon is the only large moon among the inner planets. Mercury and Venus have no moons at all, and the moons of Mars are just two tiny chunks of rock. The lunar surface. Although the moon is the brightest object in our nighttime sky, the lunar surface is actually quite dark. The albedo of the moon, the amount of sunlight that its surface reflects, is very small, only about 0.07 or 7%. In contrast, Earth has an average albedo of nearly 0.31, 31%. The sunlight that is absorbed by the surface of the moon is responsible for the extreme differences in temperature on its surface. Because the moon has no atmosphere, sunlight can beat the moon's surface at temperatures as high as 400 K or 127 degrees Celsius. During the absence of sunlight, the moon's surface temperature can drop to a chilly 100 K or negative 173 degrees Celsius. The physical surface of the moon is very different than that of Earth. There is no erosion on the moon, except for surface creep and water caused by recent impacts. Because it has no atmosphere or flowing water, the surface of the moon consists of several features. Regions called highlands, shown in Figure 28.8a, are light in color, mountainous, and heavily covered with craters. Regions called Maria, singular mare, shown in Figure 28.8a, are dark, smooth plains which, on average, are 3 kilometers lower in elevation than the highlands. All of the craters of the moon are impact craters formed when objects from space crashed into the lunar surface. The material blasted out during these impacts fell back onto the surface of ejecta. Some craters have long trails of ejecta called rays. They radiate outward. Rays are visible as light-colored streaks are shown in Figure 28.8b. In contrast to the crater-covered highlands, the surface within Maria are quite smooth. However, the Maria do have a few scattered craters and rilles, which are meandering, valley-like structures, as illustrated in Figure 28.8d. In addition, around some of the Maria are mountainous ranges shown in Figure 28.8c. Why does the moon have many craters while Earth's are few? Early in the formation of the solar system, Earth was bombarded just as heavily as the moon, but erosion on Earth eliminated traces of all but the younger craters. On the moon, craters are preserved until one impact covers another. Composition. The moon is made up of minerals similar to those on Earth. Most silicates, mostly silicates. The highlands, which cover most of the lunar surface, are predominantly lunar breccias, which are rocks formed by the fusing together of smaller pieces of rock during impacts. Unlike sedimentary breccias on Earth, most of the lunar breccias are composed of plagioclase feldspar, a silicate containing high quantities of calcium and aluminum, but low quantities of iron. The Maria are sedimentary basalts that differ from those on Earth and they contain no water. History of the Moon. The entire lunar surface is very old. Radiometric dating of lunar rocks from the highlands indicates an age between 3.8 and 4.6 billion years. Based on the ages of the highlands and the frequency of the impact craters that cover them, scientists theorize that the Moon was heavily bombarded during its first 800 million years, which resulted in the breaking and heating of rocks on the surface of the Moon. This formed a layer of loose, ground-up rock called regolith on the surface of the Moon. The regolith averages several meters in thickness, but it varies considerably depending on location. The Maria, only slightly younger than the highlands, are between 3.1 and 3.8 billion years old. After the period of intense bombardment in which the highlands formed, lava welled up from the Moon's interior and filled in the large impact basins to form the Maria. The Maria have remained relatively free of craters because fewer impacts have occurred on the Moon since the time when they formed. However, flowing lava in the Maria scarred their surfaces with rileys, which are much like lava tubes found on Earth. During the formation of the Maria, the lava often did not fill the basins completely. Instead, the rims of the basins remained above the lava and formed the mountain ranges that now exist around many of the Maria. As shown in Figure 28.9, there are virtually no Maria on the far side of the Moon, which is covered almost completely with highlands. Scientists hypothesize that this is because the crust is twice as thick on the far side, which would have made it increasingly difficult for lava to reach the lunar surface. You will determine the relative ages of the Moon's surface features in the Mapping GeoLab at the end of the chapter. Tectonics on the Moon. Mountain ranges around Maria were formed by impacts, not technically as mountain ranges on Earth's are. But is that enough evidence to conclude that the Moon is not technically active? Scientists infer from seismometer data that the Moon, like Earth, has a layered structure, which consists of the crust, the upper mantle and the lower mantle, and the core, as illustrated in Figure 28.10. The crust varies in thickness and is thickest on the far side. The Moon's upper mantle is solid, its lower mantle is practically molten, and its core is made of solid iron. Seismometers also measure moonquake strength and their frequency. Although the Moon experiences a moonquake that would be strong enough to cause dishes to fall out of a cupboard approximately once a year. Scientists theorize that the Moon is not technically active. The fact that the Moon has no active volcanoes and no significant magnetic field supports scientists' theory that tectonics are not occurring on the Moon. Formation theories. Several theories have been proposed to explain the Moon's unique properties. One of these is the capture theory, which proposes that the solar system was forming a large object ventured too near to the forming Earth because became trapped in its gravitational pull and formed into what is now the Moon. One problem with this theory is that something would have to slow down the passing object for it to become trapped inside of continuing on its original path. Another problem with the capture theory is that Earth and the Moon are composed of very similar elements. If the Moon has been captured, we would expect the crust of the Moon and Earth to have different composites rather than similar ones. Another theory, called the stimulus formation theory, accounts for the problems with the capture theory. According to this theory, the Moon and Earth formed at the same time and in the same general area, and thus the materials from which they formed were essentially the same. Also, because they formed in the same general area, the Moon did not have to be slowed down to become gravitationally trapped. This theory does not account for the different amounts of iron in Earth on the Moon. However, the Moon is iron poor, which on Earth, iron is relatively abundant. The most commonly accepted theory of how the moon formed, the impact theory, can explain astronomers' observations as a whole. Computer models indicate that the moon formed as the result of a gigantic collision between Earth and a Mars-sized object about 4.5 billion years ago, when the solar system was forming. As a result of the collision, materials from the incoming body and from Earth's outer layers were ejected into space, where they then merged together to form the moon, as illustrated by Figure 2811. This model accounts for why the moon is so similar to Earth in chemical composition. If this model is correct, then the moon is made up of material that was originally part of the Earth's iron deficient crust, as well as material that was once part of Earth's mantle. Heat produced by the impact would have evaporated any water that was present and resulted in lunar minerals lacking water. Despite scientists' uncertainty about how the moon formed, we do know that it plays a vital role in the sun's Earth system, as you will learn in the following section.